My name is Isaac Berry from Berry Science Lab. And welcome to the F equals MA exam 2020B question number 5. So we've gone through the last 4 questions pretty smoothly, so here's the 5th one. And this one, even though it has to do with elliptical orbitals, surprisingly has nothing to do with Kepler, unlike the next one. The next one. So basically, let's say we have a star, and this star has a mass m. And then we have a little tiny moon or random satellite, and this has a mass of little m. And this tiny satellite goes around in an elliptical orbit. Right now it's at I don't actually know how to name this point, but it's at its farthest point in the orbit from the sun, which can be expressed with distance r. And the question basically says, so let's say it's traveling at a velocity v right here. So the question says, what is this distance right here between the closest part of the orbit and the star? If this dust speck has a mass of m, a velocity v, is farthest from the sun at a distance r, and the sun has a mass big M. So it's basically telling us, express this distance, which we're going to call r closest, or RC. It's asking us to express RC in terms of M, V, R, and the big M. Now, I was scared initially of this problem because I thought, elliptical orbits, that must mean Kepler's laws. But in fact, this has nothing to do with Kepler's laws because I don't remember that kind of stuff. So instead, the 2 things we're going to be using is angular momentum conservation and mechanical energy conservation. Now, we know we call this RC, or R closest. Now, we can call its velocity here V closest. And a thing that we have to note here is, yes, I know this is one of Kepler's laws, but still, one of Kepler's laws, if I remember correctly, is basically saying if you have a line from here to here, and a line from here to here, then, never mind. That's not the Kepler's law that I was remembering correctly. But it basically says that the velocity when you're farthest from the sun is really tiny, while the velocity when you're closest to the sun is really large. So that means VC is way bigger than V. And as you can see by this diagram, RC is way smaller than R. And let's also say this is a mass MC. Just kidding. It's the same M. Not doing anything involving changing mass. So M is the same throughout those two. So now, we can use angular momentum conservation, if you remember L equals mvr, to say that mv and r before, mvr, should be equal to mvc and rc. And we can cancel out these fellows. And now, we want to find RC, but this equation just won't do it for us, because if we find RC using this, gives us VR over VC. That's not, and using VC in our answer when it explicitly told us not to is not satisfactory. And that's where the second part of this problem, if I could get the eraser to work, comes in. Mechanical energy conservation. So, mechanical energy conservation, you should all know it by now, says that U plus K initial equals U plus K after. In this case, U plus K at our farthest positions is equal to UC plus KC, which is at our closest position. Now think about it. U is going to be, since we're talking about space, not like close to Earth, we're going to say Z, big M, little m, over R. And where you put the minus. But UC is going to be minus G mm over RC. And since RC is way smaller than R, that means UC is going to be way bigger than U. And similarly, since KC is half MVC squared, and K is just half MV squared, since VC is way bigger than V, KC is going to be way bigger than K. So that means that this part of the equation is essentially 0 compared to this part of the equation. So we have 0 equals UC, which is going to be MGH, or I'm bugging out, that's near Earth, but far from Earth, we minus G big M little m over R sub C. And with that, K would just be half MVC squared. And now all we have to do is input a formula for VC derives like this, VR over RC, and then plug it in here. And you might say, well, we still have RC here, so isn't that dissatisfactory? Well, remember, we're solving for R here. So, expressing this whole thing in terms of R, C is going to massively help us. So we have VR over RC, right? Yeah, gotta make sure that's correct. Okay, VR over RC, and remember, this is squared, this is squared, this is squared, because we squared this entire thing at the beginning. So now, here's the little trick that we can use. We can multiply everything by RC to get rid of these weird denominators. If we multiply everything by RC, we get 0 over here, minus GMM plus half M times V squared R squared over just RC, which means now this is very easily solvable. All we need to do is do a little bit of rearranging. First cancelable term is, you should be able to see it immediately, little m. Then we just get 0 is equal to V squared R squared over 2RC minus G big M. And now we can just bring a GM to the other side and get GM equals V squared big R squared over 2RC. I forgot the algebraic derivation part, so I'm doing all of this off the top of my head. And then 1 over GM is equal to 2RC over V squared R squared, which means RC is just V squared R squared over 2GM, which looks about right. Yep, and that's our answer. And RC is approximately, because remember, we expressed U and K before as 0 when they really were a little more than 0. It's approximately V squared R squared over 2GM. And they said which one is the closest, I believe, anyway. So that's our answer. Hopefully, if the official solution didn't do it for you, this one was a little clearer. Thank you, everyone, for watching.